University Technical Malaysia Melaka SEEP 2018. So without further ado, please welcome Professor IR Dr. Badr Hisham bin Ahmad to present his webinar. Please welcome, Prof.
Okay, thank you very much, Dr. Saidatul. Okay, thank you also for the brief introduction of me. So, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. To everyone who are attending this webinar, good afternoon. How are you today? With our new norm, we have to do everything via online, even our meeting, our classes, and examination is through online. So, I hope you can bear with me with next 1 hour, I think, the most, to listen to the sharing, for the sharing. Okay, thank you also to IEEE Malaysia section AP MTT EMC Joint Chapter Malaysia for the opportunity given to me. So the topic that I will share with you today is theory and design of substrate integrated waveguide, in short SIW. So actually, AP MTT EMC was I was the previous chair of this section. So I was really happy, really proud of being part of IEEE AP NTTMC Joint Malaysia chapter. It gave me very wide experience. Get to know many talented talent in the world. So now, but unfortunately, I have gone through that phase and pass it down to uh, young and vibrant talent, Dr. Azremi and team. So good luck to you guys with AP MTTMC chapter. So okay, now we let's proceed with the slide. Okay, Dr. Sai, next. So before I proceed to the main content, let me share with you a bit of my university, which is University Technical Malaysia Melaka, or in short, UTEM. We are actually located in Durian Tunggal Melaka. We have a slogan which is very close to Melaka state, which is Melaka is UTEM and UTEM is Melaka. And for your information, we have two campuses, which is one is in Durian Tunggal Melaka and the other is at 𝐓𝐡𝐞𝐨𝐫𝐲. And we are located somewhere about 150 kilometers away from Kuala Lumpur, and it is about 1.5 hours drive by car. If you're not exceeding the speed limit, then it's okay. It's about 1.5 hours. But if you plus the traffic jam, maybe it took you about 5 hours in the normal circumstances. Okay. So next, Dr. Sai. And UTEM is actually established since year 2000. And UTEM have 8 faculties altogether and 86 program, which is PhD, Master, Bachelor and Diploma program. We have a total of 10,930 students altogether, active students. About 677 is international students. And our niche area basically is advanced manufacturing and computing technology. Sorry. And as for our graduates, we have graduate employability about 86%, which is above average. We have a total alumni of over 26,000, that is since year 2005. And most of our graduates are certified with professional certificate, for example, Microsoft Data Science, Cisco, Oracle, Lean Six Sigma, etc. And we have a very good relation with industry. We have about more than 100 industry partners. And we have also industry labs located in our campus. For example, Samsung IoT Lab, ST IoT Lab, Cisco Academy, and Oracle Academy. And our alumni also very active, engaged with the community and industries. And as for human resource, we have a total number of 800, over 800 academic staff, and many of which have professional certificate, for example, chartered engineer and many more. And our staff also, majority have PhD, more than 50% have PhD, and we have academics also with international recognition and been appointed as an experts and also consultants, for example OIC cert, blockchain technology, and CTFL cert. Okay, and also we have because we just received a new vice chancellor, so our new team now is Tunai, uh, whereby we very much enclose or close relationship with industry, consultation and so on. So the concept Tunai is very close to our heart. Basically Tunai in Malay is like cash reward. So instead of receiving, now we are giving back to the community, to the industry, to the alumni, okay, to the NGOs, giving in terms of not only knowledge but also collaborate, and we can work together more than what we can promote lah. Okay, next. Okay, and as a summary, I just would like to summarize the talk today in terms of the abstract. Basically, this substrate integrated waveguide was first being introduced by a professor from Canada named Wu in 2001. So this concept is very much useful, whereby it integrates the image guide, non-relative dielectric waveguide, and it synthesizes it inside the dielectric substrate, and it uses the rows of dielectric vias or metal holes as a replacement for a waveguide wall. So it's a very good ideas in terms of you can replicate or you can perform different kind of microwave devices, for example filters, resonators and antennas, to adopt this new technique and technology. Okay, so it is also have a fabricate using standard PCB process and have a very simple transition. So this talk will basically discuss about the application of basically microwave and millimeter wave. Then we will go into the theory and design of the substrate integrated waveguide, and proceed with a few design examples that we have done. Not much, but there is some, and also we will finally discuss about the opportunities and challenges for the substrate integrated circuits. Okay, next. And as for the content, I would like first to outline the talk, which is firstly it will separate into five main topics, which is start with the background of microwave and millimeter wave engineering applications. Then I will go into our main content for this talk, which is the theory and design of SIW circuit technology, and I will show a few design examples related to substrate integrated waveguide, and then I will end the talk with the opportunity, conclusion, and also challenges. Okay, next, Dr. Sai. Okay guys, I think you have familiar with this graph and figures. Basically, radio frequencies is an oscillation rate of an alternating electric circuits or voltage or of a magnetic, electric and electromagnetic field or mechanical system in the frequency range from about 20 to 300 gigahertz. So the more than that, you can say it is in terms of radiating signals or ionizing signals. So it's a very high power, and in terms of it cannot be exposed direct to human skin. Even as you can see, the gamma ray and X-ray very penetration. Even it can penetrate through steel and so on. So it requires a different technology. So if you starting from the low frequency or in kilohertz, increasing slowly in terms of the waveguide, the wavelength will start to decrease. Okay, so the low frequency would have the wavelength of the size of the building, basically in terms of kilohertz. So this picture shows we are in the frequency domain. So the left hand side picture also shows the wavelength is big. Okay, like I said, as big as the building, and the dimension is also big. So our focus for today will be on the wavelength for the size of the butterfly. So if you can see there, the picture shows butterfly size basically is the frequency of microwave and also millimeter wave, which is the region of microwave and millimeter wave frequency. And also the terrestrial microwave communication links are limited by the visual horizon for about 40 miles only, about 64 kilometer, and most of the application that we use every day is within this range in millimeter wave and microwave. Okay, so at the high end of the band, for example, the high end, so it is very much absorptive in nature. It is absorbed by gases in the atmosphere, so it limit the practical communication distance to around only a few kilometers. Okay, for this talk, we will only focus at the frequency of within the butterfly wavelength. Okay, so basically it's a typically it is a line of sight punya communication. Okay, okay, next. So as you can see, how far does the microwave application have been developed over the years? Okay, basic microwave transmission lines. One of them is basically a waveguide. So waveguide basic concept is the first time it was being used is in World War II, whereby and most of the work done basically it was experimentation and not much interested in wireless communication at that time. And the picture that I show you in the slide on the left hand side is called AN APS4. It is actually a air surface model H. This is the what we call the radar, intercept radar used by American and British during World War II. So you can see the APS4 is operated at X-band frequency at 3 centimeter size wavelength compared to the 10 centimeter S-band. So this model was smaller compared to that era, during that era, which is S-band. So this allowed the antenna to be greatly reduced in size because we are in the X-band region, and the whole the unit can fit into a single streamline firing that could be mounted to any aircraft. So it was for the purpose of war lah at that time. Okay, defense system. So after World War II, okay, after World War II, people start to use and most of the circuit basically use a microstrip. Okay, before that, if you can see the figure in the right hand side, which is we call that a low noise block down converter, or we call it LNB. It's a receiving device mounted on the satellite dish. Okay, this is the LNB block device. It was used as a satellite TV reception, so which collects the radio waves from the dish and convert it to the signal, which is sent through a cable to the receivers inside the building. And the LNB is combination of low noise mixer, oscillator, and IF amplifier. So as you can see, a very small device but have a multiple device in it. So after it is very different from what you see on the left hand side, which is very bulky and big. Okay, so this is what happened. So after World War II, we can see many applications have been produced. Okay, for microwave and millimeter wave. For example, you can see here, especially during after the establishment of the microstrip technology and also this semiconductor industry, whereby they have managed to produce many components. For example, filters, low noise amplifier, power amplifier, multiple transistors was fabricated onto one planar form. So it is very compact, tiny, and also handy. So you can see the development of devices right from the radar in terms of application in World War, war, and then after the war, it was fully developed into like commercial electronic or more on consumer development. Okay, next. Okay, I would like also to share with you this. In the first slide, I've been talking about the radiation, ionizing and non-ionizing microwave. The radiation is classified as being non-ionizing and ionizing. So non-ionizing radiation is a longer wavelength or lower frequency. Okay, it has a lower energy, while ionizing radiation is short in terms of wavelength, and it has higher frequency energy. Okay, ionizing radiation has sufficient energy to produce ions. Okay, in matter at the molecular level. So, put simply, non-ionizing radiation differs from ionizing radiation in the way it acts on materials. For example, like water, air, and living tissue. Unlike X-ray and other forms of ionizing radiation, non-ionizing radiation does not have enough energy to remove electrons from its atom or molecule. So the region where we are working at is basically in the non-ionizing punya radiation. So the application basically radio, mobile phones, and microwave oven and so on. So basically it is basically safe for us to use. Don't worry. Okay, so basically on the right hand side is a table. So if I can broadly classify, the microwave frequency range is the famous one is L2C band. Okay. It's very popular. Most of the application is within this range. Okay. So but for the X band, a bit higher. X band is especially for defense purposes. Okay, the higher order band also been looked into and also been used, but not much. So as you go to higher in frequency, especially in millimeter wave, it is getting popular nowadays. Okay, getting popular. People start looking into this. The frequency range, because not many people's being look at this. Not many applications. So the frequency is not being utilized or underused, and it is under license. We call it unlicensed spectrum. Okay, from 40 to 100 gigahertz frequency. Okay, next. I would like to share with you guys the microwave application that we have today. Okay, so let's go to the microwave application. The telecommunication signal is basically typically a bidirectional or either using TDMA or channelized. Okay, so this can be microwave relay link consisting of a transmitter which transmit a narrow beam or microwave with a parabolic dish antenna to a second parabolic dish at the receiver to communicate to a different tower to tower, also to different building. So all these we are using it currently. So communication between towers and link between different towers. And also if you look at the bottom pictures, okay, it is basically a wireless local area network whereby it links two or more devices over the short distance using a wireless distribution method, usually provide a connection through an access point for internet access. The use of spread spectrum or FDM technology may also may allow users to move around within the local area coverage and still remain connected. Okay, these wireless LAN are often used for connecting to local resources and to the internet. Okay, let's go to the microwave link. So microwave link at the top right hand corner is a system that use microwave beam or radio waves in the microwave frequency range to transmit video, audio, and also data between two locations. And this can be from just a few feet or meters to several miles, and also sometimes can be kilometers. And also, if you can go to the bottom right, you can see the CAS, which is the collision avoiding radar. Basically, it's known as pre-crash system. It is known as pre-crash system. Usually installed in a car, advanced car. So forward collision warning system. So or we call it collision mitigating system. So it uses radar or sensors, okay, to detect the imminent crash. Okay, it can detect maybe a few in front of you objects or anything, so it can give a warning, okay, early warning, and then it can provide a warning to the driver and also to ask the driver to brake, or also take in charge of the steering so that you won't crash in any trees or anything. And also not in the picture, I would say the police strap, the pistol that, no, not the pistol, but the device that the police used to trap the speed in the highway or something. It uses the Doppler radar, which is sense a pulse and detect the shift. So so it can basically know the speed of the car which is undergone. So so there are many application of microwaves and millimeter waves in our daily lives basically. So people start to understand that there are many application that was being used today. So and it start with the defense technology. If you can see the air radar that I just showed, right into a different technology and application. This is where the microwave engineer involved in this industry. Okay, next. Okay, now I would like to show you the advancement of mobile communication that use microwaves and also millimeter waves. Okay, we start with 1G. If you can remember how big is the phone we holding, if you throw it at maybe a dog or something, the dog can die because of the heavy and also the strength of the 1G phone at that time. Okay, so it starts with 1G and then evolve into 2G, 3G, 4G, and also 5G. So what is the speed at that time? So first let us talk the speed. Okay, it was increasing from 1G to 2G, 3G, and also 5G. So from 1G, we have a few kbps, kilobit per second, and now into 4G, we have hundreds of bits, megabit per second, hundred of megabit per second. But in 1G, there is no internet line, no internet capability. But when we shift to 2G, 3G, there is an internet, but very narrow band internet. But we shift from narrow band up to wide band and so on. Now we have ultra wideband internet. So of course the bandwidth is increasing over the duration, over the period of time, and day by day we will see the increasing of bandwidth. So what is next? Okay, go to the side. Next. So next is none other than the 5G, the 5th generation. Okay, what is 5G? 5G is designed to do a variety of things, okay, that can transform our lives, including giving us faster download speeds, low latency, and more capacity and connectivity for billions of devices. Okay, especially in the area of virtual reality, IoT, and also AI. And if I can sum up the concept of 5G, we have 3 different components. First is the enhanced mobile broadband. Then we have multiple of tens of Gbps. Second is the ultra reliability, low latency. It is especially for mission critical communication. Okay, suppose there is an hazard mines, for example, mission, somebody trapped in the mines or something. So we require a machine that capable to respond in a lightning speed. So because every second involve life. Okay, so latency is very important. The latency should be very low, which means the speed is very high. So we are talking about the speed of the 5G is very high. And the third is machine-to-machine communication. We're talking about millions of sensors, industry IoT, and also massive IoT. 5G not only between mobile, okay? It's not only communication between mobile, but more than that. So if we put into a picture, okay, if we put it in a picture, for example, there is a home where you have a video calling and something. You have sensor for communication between homes, between houses. So there is application that part of 5G. We have also smart transport system with high-speed plane that running above us, and also we have all the application of 5G. So some frequency band are already existed, okay? And for example, microwave frequency which have the L, S, and also C band. So these frequency are ready to go lah, I would say, for 5G. But it can be exhausted, okay, because of this application, okay. So what's next? So we will look at a frequency of higher region than L, S, and C. So this frequency is the millimeter wave frequency range, which is unlicensed and unused. Okay, Dr. Sai. So I would like to share also this microwave and millimeter wave transceiver. So as I said, millimeter wave communication is very crucial. So, but what are the challenges? So many transmitters we work on is at the 2.4 GHz protocol, and the 2.4 GHz offers incredible reliability. That is no issue. Okay. The shorter the wavelength also brings less signal penetrating power, less range. However, this can be combated with the higher RF power output, so which is built into 2.4 GHz transmitter system. So the 2.4 GHz system band is pretty crowded place. So because so many applications now coming into 2.4 GHz, because it's used by more than just Wi-Fi. Okay. So all cordless phone, for example, garage door openers, baby monitors, and other devices tend to use the 2.4 GHz band. And the longer the waves used by the 2.4 GHz are better suited to longer ranges and transmission through the walls and also solid objects. So if you can see, if you move to the so how are we going? Bukan tadi, sebelum tadi. So but there is some application, if you can see, that uses microchip circuit to work in the millimeter waves. But if you try to design it, there will always be a losses, because if you try to apply microchip circuits at the millimeter waves, there would be a losses, okay, because microchip is basically an open structure, okay, and more common structure for millimeter wave, but there is some compensation of that. In other words, you can use a waveguide to design in millimeter wave region. The advantages of using waveguide basically is a low loss, and it has high power capability. It can confine all the electrical fields and magnetic fields within the structure. Okay, but as you can see, the disadvantages of using the waveguide is basically bulky, three-dimensional. So whereas all the low frequency devices that use a planar structure, so how can you combine or connect this planar and three-dimensional structure? So basically there's a challenge for us today. So we cannot carry. So can you imagine using a phone that have a waveguide punya filter, waveguide punya power amplifier? What would that be? What would be the size of your phone now? It will be too big to carry inside your pocket also. Okay, so it is very not so practical, I would say. Okay, so but the challenge now is to think what are the replacement of a waveguide, so that we can stay along in the millimeter wave territory, and also what are the replacement of microstrip technology or microstrip circuits, whereby you can maintain the planar but have the advantages of higher Q than the microstrip, have better in terms of losses than the microstrip, and so on. Okay, so for waveguide there is a catch also, okay, because not we can say it's high performance and so on, but the catch is the transition is hard to do and it's not easy. And of course, in microwave, whenever you have difficult complex structure to do, the cost would be high, very high. Okay, next. So what the picture shows us in the slide is basically the typical concept, the typical transition that involve within the microstrip and also the 3D waveguide, for example. So if you can see, it is very high manufacturing cost and also complicated. It's not easy. So, and also the dimensional is in millimeter structure because you are working in millimeter frequency range, and also the size is basically in millimeter region. So a small fracture or error dimension would degrade the performance, okay, of the overall system. So the conclusion is so this concept is basically involve high manufacturing costs, and it require complex transition. Okay, so basically, so what are the solution? So next, so the solution is substrate integrated waveguide, or SIW, I would say. So basically, the idea of SIW is in 1994, the origin idea, because it is through a Japanese pattern. As you can see, it uses at that time the concept of plated through holes is very popular, and then they put plated through holes through a wall, and then it demonstrate the wall of a waveguide, and it acts as a side wall, and also it can act as a planar structure. So if you can fill the holes in the waveguide with the dielectric, so it become planar. Okay, so people start using multi-layer configuration, laminated waveguide, parallel plate waveguide. So it is good candidate for high frequency application. Okay, so if you can see the middle structure is a laminated wall used for the collision avoidance systems, and the right hand is the post wall wireless LAN, okay, that use in 60 GHz, and also in car avoiding system that have the frequency range of 77 GHz frequency. Okay, next. So the technology background, waveguide, as we know, is very bulky, and the SIW is basically the bridging the gap between the rectangular waveguide and microstrip line. Okay, it can generate different circuit in planar substrate, which you can use to handle your devices. As you can see here, which stated in the notes, the waveguide is basically not suitable for low cost mass production. It is very high cost, and it is a problem with connectivity between planar and non-planar, and it's bulky, so very big, because nowadays we are moving into a very small, compact, and handy. So it's not very suitable. So basically, SIW, or substrate integrated waveguide, is the solution for the future. Okay, next. So how does the substrate integrated waveguide look like? Okay, the first thing that you can see is the transition between SIW and microstrip line. It's very simple. As you can see, it just use a taper, microstrip taper, or the coplanar. Okay, coplanar technique. What are the advantages? Okay, if you put a vias, rows of vias between the structures, it act as a shielded structure. It can shield or confine the transmission lines or fields within its region. So taper, and also you can use step impedance also as a displacement for taper. So two-sided copper cladding. So we can straight away can implement it, because it uses standard PCB process. So it's so as you can see in the picture, it has the advantages is low loss. Okay, because basically the wave, I will show later that the wave is actually confined within the rows of vias, and it has a high Q transmission line, because of course it better performance than the microstrip, and it has self-consistent electrical shielding, because it shield from penetration from outside, and also because the nature of the signal propagate inside the waveguide or SIW is different from the one that you have in microstrip, and it's easy to fabricate, and also integration is easy to integrate with other planar devices. Okay, next. So there is other types of substrate integrated circuits. The complete family of SIC, substrate integrated circuit, which is the first one is substrate integrated waveguide. The second one is substrate integrated slab waveguide. Okay, the third one is substrate integrated non-radiating dielectric guide. Okay, next. The fourth one is substrate integrated image dielectric guide, and number 5 is substrate integrated inset dielectric guide, and lastly is substrate integrated insular guide. So as you can see, these 6 are very much part of the family, part of the concept of substrate integrated circuits, but the most popular is substrate integrated circuit or substrate integrated waveguide, the first structure or first figure that I show just now. Okay, next. Okay, now we go to the substrate integrated waveguide structure. Also, basically, the first evolution happened in SIW technology. SIW is the most popular choice, whereby it has easy to transplant the existing technology, and it has a mature technology and design structure, which is PCB, and it has a higher Q, higher Q, of course, lower than the waveguide, but it is higher than the microstrip. And the mapping from SIW to conventional rectangular waveguide is almost perfect from a single mode operation, and hence all the theoretical framework is directly applicable to this structure. And also the transition structure makes it, for example, use a taper and coplanar waveguide depending on the nature of the application and so on. Okay, next. Okay, now we going into the propagating modes of the SIW. So there are bias and gaps. If you can see the propagation nature. So the current path distribution is, if you know the existing SIW, sustain the fields. Sustain is sustaining the fields within the via, and the field consists of 2 rows and confined or contained within the two rows of vias. Okay. And the SIW have limited number of propagation modes. Okay, that's these advantages. That's the disadvantages. But for those mode where the current distribution in the wall is along the perpendicular to the direction of the via, which is the direction of the vias, which is in the direction of vias, therefore those modes cannot sustain in the SIW, because the different modes would be escaping through the nature of propagate is different from the only certain numbers of modes capable of transmitting. For example, SIW can only support TEM0 mode. Okay, unlike the waveguide, where it can support any mode and have unlimited modes that can propagate through it. Okay, next. Okay, this is the study that was being done by previous researchers, whereby the dispersion properties of the substrate integrated waveguide are rigorous, obtained by using this BIRME method, obtained from the Floquet's theorem. From this analysis, we can see that SIW basically have the same guided wave characteristic with the conventional rectangular waveguide. Okay, empirical equations are derived from the calculated dispersion curve in order to estimate the cutoff frequency of the first 2 domain of the SIW. And to validate this analysis, the result have been fabricated and measured, and the experiment and also the theoretical result was shown in the picture in front of you. Okay, next. So if I can share with you the SIW design theory and how to design it. Basically, the propagation constant after the cutoff frequency starts. So not only it is the function of width, but also with diameter and also pitch. Okay, so from this data, people starts to do the the design and derive the equation. So the best way to know is the width of the SIW is different from the width of waveguide, and also microstrip. It is called the effective width. To take into account the effective width, we use the equation that shown in the slide. Okay, next. Okay, so the graph shows that it is very important to choose the parameter that you want to use. Basically, the unshaded region is the unwanted region. So basically, you use the shaded region. So the shaded region, choose any parameter that within within that region. So if there is more bias, so if you can put more bias at the SAW or substrate integrated waveguide, this is the disadvantages, which is the substrate will break. If you put the continuous wire and very closely spaced, it will break. And if you put the gap, make the gap higher, the signal or the transmitted signal will leak to different through the gap. Okay, next. So this is the design example of substrate integrated waveguide transmission lines. So if you can design it with a substrate called Roger-Duroid 5880, which have the relative permittivity of 2.2 and the thickness is 0.787 and the loss tangent is 0.0009. Basically, if you can design it with the equivalent width, height, and the size of the diameter, size of the post, okay, size of the post, distance between the posts, and the length of the SAW, you can get this as a normal transmission lines, and it is very good also, very low loss, and if you can see the current distribution or surface current, how does it propagate into. So this is, I believe, the propagation signal is basically TE10 mode. Okay, next. So next is the substrate integrated waveguide cavity. You can also calculate the cavity within this SAW. So if you can use this the equation that was laid out in the slide. So it has 4 rows, basically 4 lines of rows, and it has equivalent of effective length and width. So this is also an example. If you can calculate the size of the cavity with still use the Roger, and also the width, the height, and also the diameter of the wires. So you can basically calculate the modes exist in the cavity, which is for the first mode, which is at the center of frequency, which is 9.4. The second is 14 gigahertz, and the third is basically if I can see, is about 15 gigahertz. Okay, next. So okay, for the cavity, the first 3 modes that propagates is basically, the first mode is called the dominant modes. Typically, we can use this mode to excite an antenna. So because, as you know, bidirectional antenna is a very popular antenna to be used, but unidirectional antenna is the most popular one. So we can use a reflector or cavity behind the slot, so which is, we can straight away implement the concept of SAW in a planar form. Okay, next. So for this slide, I would like also to share the transmission losses that occur in the SAW. So basically, Dr. Sai, next. The transmission losses. Okay, so basically what you see here is the characteristic of a electromagnetic signals that propagate. Okay, decomposition, if you can see, every electromagnetic signal have gamma equals to alpha plus j beta, which is basically the real and imaginary part, and the oscillating electric and magnetic field also we have here, magnetic field and also electric field. And from here you can see the beta is basically the propagation constant, okay, the beta, and alpha is basically the losses that was created that was created by the nature of the technology. For example, this we are talking about the common losses that we face in the microstrip. For example, we have lambda c, lambda beta, we have lambda d also, lambda g, and lambda r. So basically this lambda c, for example, this is losses that created due to the external metal conductivity, and lambda d is the losses that was created due to loss tangent in the dielectric filling, and also lambda g is basically the losses due to the conductivity of the dielectric medium filling, and lambda r basically is the losses due to the radiation. Okay, but the decomposition, this composition is valid to all transmission lines. Okay, but for rectangular waveguides, okay, the attenuation due to radiation and substrate conductivity, we can say it is negligible. Basically, lambda c and lambda d we can remove, we can ignore. Indeed, usually the substrate is an is an insulator such that the lambda g basically is equals to 0. In that way, all the wall thickness is much thicker than the skin depth of the signal, so no radiation will appear. So this is in fact one of the advantages of closed waveguide compared to the open line such as microstrip. So out of these 4 losses, only 2 are contributed to losses for waveguide. So as you can see, the SIW is replicate what the waveguide is. So we have out of 4 that contribute to losses in microstrip, but for SIW we have only 2 losses that contribute to the SIW. So the SIW shows a comparable or lower losses compared with other traditional planar structures like microstrip and coplanar lines, especially at higher frequency. If the substrate is thick enough, the losses are dominated by the dielectric behavior of the substrate. Okay, next. So as you can see, this so it is noticeable that lambda c is directly linked to the substrate thickness, and also b is thinner than the substrate, and the higher the conduction losses. So this can be explained by keeping in mind that the ohmic losses are determined by integrating the current density on a path closing the waveguide walls. So on the top and bottom of the horizontal metallic plates, the current is scaled by 1 over b. Okay, due to the modification of the intensity of the plates, and when b is increased, the field intensity decreases. Okay, because it is inversely proportional, as well as the current. So, but in the vertical wall, the variation is Js square, which is the surface current density, compensated by the lengthening of the integration path C, and as a result, the contribution of the vertical bias to the conductor losses is unchanged with B, and this is the reason why there is 2 terms in the expression of lambda C. Okay, the first is independent of B, while the second one is varies with 1 over B. Okay, another key point in the conducting losses experienced by SIW is linked to the roughness of the surface. Okay, that appear due to the synthesis processes. So this roughness decreases the effective conductivity of the metallic walls and subsequently increases the losses. And if we can observe, this observation is of crucial importance for the design of the SIW, as they are integrated on a very thin substrate. So for this case, the contribution of the conduction losses on the global attenuation is predominant. Okay, next. So the third one is the SIW attenuation due to dielectric substrate. The attenuation due to the dielectric behavior. Okay, so we can prove that by making the Taylor expansion of the product, which is square root of a square plus x square. For x is very much bigger than a. The propagation constant is given by the equation that in the slide. So where tangent delta is the loss tangent of the dielectric substrate, and this approximation is correct if the tangent delta is much bigger than 1. And we can see also for the case of microwave electronics, which is at 10 GHz, we have tangent delta to be 0 in air and in Teflon we have 1.5 times 10 to the minus 4 in Teflon, and we have then we can follow the identification that was made. Okay, this relation is correct for both electrical and magnetic transverse modes. And also the dielectric losses lambda d, which is depend on the substrate and not on the geometry. Okay, lambda d. Okay, so unlike the conduction losses, lambda d is not influenced by the substrate thickness, but it is transpires that the only way to reduce lambda d is consists of choosing a template with better dielectric properties. Okay, so which is the lower the loss tangent or tangent delta, and then the would be the lower the losses or attenuation. Okay, next. So this one is related to SIW attenuation due to radiation. As you can see, the D stands for diameter, S is spacing, and A is distance between the vias. And because of the vertical walls of the SIW is not continuous, the radiation leakages may flow between the vias, and this leakage can significantly affect the transmission quality if the vias geometry are not chosen carefully. Some studies have been conducted to describe or predict and reduce the radiation losses. They have resulted in some simple geometry, which is shown in the figure lah, which is the spacing should be. This is a design rule lah for to minimize the losses due to radiation. So the spacing S should be less or equal to 2D, and also the D, which is the diameter of the vias, should be less or equal to A/5. Okay, and the geometric parameter of the interest are the diameter D and the spacing S, and the center between the vias, center to center, is A, and they must be tuned. Dia bukannya once you calculate it become perfect. No, you have to tune also. In such a way, it is approximate the behavior of the continuous metallic wall. Okay, and the spacing of the vias has to remain small compared with the diameter. Okay, which the diameter must be small compared to the waveguide width to keep the radiation losses reasonably small and the recommended values. Okay, given by the given by the condition of the SIW formula. S less or equal to 2D, and also D is less or equal to A/5. Okay, next. So this is the few example that was produced in our labs. So basically, this is the first design is basically a transmission mode, using a standard ladder network technique to produce a band stop filters. So this is fabricated on the Roger Duroid substrate. In the middle also we have we call it even an old mode band stop filters. It use in the middle there is a 5 order SIW bandpass filters. It's connected to a 2-stage branch line coupler. So the idea is to convert the bandstop from bandstop response. From bandpass response, because in the middle is bandpass filters, into bandstop responses. And in the in the right hand stage is also basically an even pre-distorted technique to produce a bandstop response also. But as a summarization of the design, it shows that SIW technique are capable of implemented. Okay, the original idea was using different technique or different technology to fabricate, to calculate, but you can use the same technique to calculate, to simulate, but in terms of fabrication of the devices, you can opt for SIW technique. Okay, next. Okay, now I'm reaching almost the end of the slides. The opportunity of the substrate integrated waveguide is basically a mixed integration, different waveguide, different structure, different devices. Okay, high density multi-layer integration is also possible, and we have active and nonlinear integrated waveguides. Okay, so and also monolithic integration of the integrated of all the circuits, okay, on the substrate, including the antennas. Okay, next. Okay, as for conclusion, we know that substrate integrated circuits, or SIC, is for low cost and high density RF and millimeter wave fabrication, and it can hybrid in terms of design platform. It can integrate between different technique, different planar. We can marry them together, and potential of monolithic SIC towards a system on a substrate. So ultimately we want to produce a system on chip. So basically the idea of SAW is capable to realize this. And we have also substrate integrated circuits that open up new possibilities to implement a novel circuits, a new circuits that has a very low profile PCB structures, and also new technology. It can be a major player to meet the current technology requirement for microwave and millimeter wave spectrum. So because now we talk about 5G and so on, the C-band is opted or modified with the current technology or standard application or standard devices that are available, and millimeter wave basically installing new facilities. So it requires new, of course, resource in terms of money and so on. So it's in an open debate to implement and everything. But SAW is here to stay, to be applied, to be investigated, to be studied by basically in the microwave world. Okay, next. So this is the reference that was used. Next. Okay, I think I have reached the end of the slide. Thank you so much, Dr. Sai Datul Noliana, for helping me controlling the slides. I don't know what I would do without her help, without Dr. Sai help. So thank you very much for the opportunity. Now we open to any question and answer. If I can help you, if the answer is within my knowledge, I will try to answer. If not, then maybe we can have different platform, different discussion medium, for example, in email or WhatsApp.
Right, thank you, Prof.
Thank you.
We have one question basically from the chat room. It says from Abdul Kadir. Assalamualaikum, Prof. Is it possible to design a dual band or multiple branch line coupler using SIW technology?
Okay, thank you very much, Dr. Kadir. I presume you are a lecturer, maybe because you are interested in SIW dual band. I'm sorry, what's that? Dual band branch line coupler?
Yeah, dual band or multi-band branch line coupler.
Okay, okay. As you know, during my years of research, actually I have managed to design two-stage microstrip branch line coupler, two-stage. So basically, and also I've seen also read some article related to SAW branch line coupler. So basically, it is not impossible to design a two-stage branch line coupler using SAW technique. Of course, you can, but bear in mind, if you have it in low frequency, the size would be big to fabricate. But if you move on in millimeter wave, higher frequency, the size will be reduced and just nice in terms of the size and so on. Yes, it is possible to design SAW branch line coupler.
All right. There is one more question from Dr. Siti Zuraida. She would like to ask, what is the best method for the fabrications of SIW components to ensure the simulated performance similar to the measured results? Is it possible to have multi-layer design using SIW technique?
Yeah, doctor, as I shared with you in the slides, there are actually 6 different type of substrate integrated circuits. The most popular one is substrate integrated waveguide, but there are possibilities whereby you can integrate different layers of metals within the substrate, but it involves really complicated, and your software should be capable of doing this, because we know that ADS or momentum should be very limited to only planar structure. You can design SIW in ADS, but limited to top and bottom metal structures. But HFSS or CST is another option whereby you can structure different layers into different layers of SIW, so multi-layered SIW, I would say that. So that's why there is one design, one research that produce filter using SIW filter integrated with antenna. So basically, the antenna feed a signal to the filter to be filtered. Okay, so it is and involve a few layers of SIW in the same substrate. So basically, I would say first choose a really good substrate. Of course, if you use Roger, the output will be marvelous because it's a low loss substrate. But I believe for standard university punya apa nama proof a concept, just use a cheap microstrip, just use FR4, just for the sake of prove the concept. But for industry, yes, you the result worthwhile by using Roger, for example, because FR4 is very cheap. Just because for us in the university, we only concern with proof of concept. It is, if it is capable of using FR4, why not Roger? So it's open, still open to discussion and proof of concept. But the same technique, I think the challenge now in university, because the equipment to fabricate SIW is not cheap, it's expensive. It use LTCC technique. So I think it's available in, I think some of the our GLCs in telecom. I think there are equipment that capable of fabrication. So but for normal people, like normal researchers who wants to fabricate SIW, why not you do normal drill? You drill a padded hole and you fill it with metal. You fill it with the solder iron. So basically, but you have to be really careful and take care of your punya apa nama because as you know, solder iron is very poisonous. The gas produced and the heat produced by the solder lead also very high. So be careful. Okay.
Assalamualaikum Dr. Bat.
Waalaikumsalam, Prof.
I think it's very interesting, okay, for your SIW though. Okay, regarding you mentioned about the FR4, I think for the high frequency, definitely it's not suitable to create this kind of structure lah, definitely. Especially if you talk about 5G, ya. Kalau 5G tu 26, 28 millimeter wave kan?
Betul.
Quite high. But just my question is, what do you think about the metal wires and just a free space without any metal?
Okay.
What do you think about this? This technique? Because I don't know whether you are using the metal wires, right, in your SIW.
Betul.
And then we also can use just a free space without any metals to be connected, just a hole, to make sure that the thing is working as the SIW. So what do you think about these two? Because we try, metal is being shorted everywhere. I don't know.
Yes. There is one way to replace metal wires. You can use, like Prof Kamal said, you etch the area that you want to assign as a metal wires. So it would be looking like a drain, a series of drains along the width.
A series of the hole without any metals.
I think it is not possible because you somehow have to duplicate the side walls of the waveguide. If you're not able to put these side walls, the signals or the signals that propagate inside the metal would not be TE or TM. It would be like on normal TEM, just like microstrip lines only transverse electromagnetic signals will propagate without the metal bias or metal drain, because Prof. Kamal said just air. Air is, I would say, is non-conductive material. It would not be performing as good as metal in terms of conducting and so on. The reason why it put a series of metal drain or metal bias to confine the signals of TE or TM that propagate inside the SIW. That's the reason. If you put there is no metal, just air, I believe first it would not, the signal would not propagate TE and TM. This only TM that propagate inside the microstrip, and the signal will penetrate or through radiation, through copper losses, dielectric loss, and so on.
But I think if we put metal, yes, of course, that's that one I agree with that. But I think if we just make it like just a metal, sometimes the metal will be shorted with the structure itself, and nothing happen.
Oh.
So that's why we need to put just a bias, just a hole with
Okay.
just a free space.
Okay,
And
Prof.
when we do that,
Yes, I think if you manage to do that, would be a biggest breakthrough in the world of microwave. But it's an open debate. You can try it in the lab, in the experiment, without etching or put any bias, because you're afraid the metal bias will short short to the device and nothing happen, right?
we did
So
already. We can get the result. So that's why
yes,
maybe the concept of SIWA is not correct, because SIW we need to have, this boundary between these
yes,
two metals.
no,
Never mind, we can try have a look because
yes.
we try to do already with the metal, but it's already
Ah,
being shorted. The
oh.
antenna itself.
Oh, maybe I should have take a look to this structure that Prof. Kamal say, and maybe I can help you in terms of explaining what really happens, because my area is yes, as you can say, is substrate integrated waveguide, but truly said to you, the SIW need to have a plated holes or wire holes or the drain that made up filled with metals. Okay, sideways,
Definitely must be
left and
filled
right.
with metals. If you are
Yes.
not filled with any metals, so we cannot say that SIW.
No, no,
No.
because the metal or side wire holes will act as a boundary limiting wires that limit the wave, the field wave, H field and E field from propagating outside the structures. If not, it will leave the structures and would be a losses to the device.
Okay. Thank you. That's right.
Thank you, Prof.
Okay, Prof. Thank you, Prof. Dodo, Prof.
Okay.
Okay, like a lot of questions. I get like two
Uh-huh.
more questions.
All
One
right.
is from Muhammad Inamabsi. Sorry if I
Okay.
pronounced your name wrong.
Yes.
The question is that is there any upper limit in terms of frequency for SIW technology, since there will be some fabrications limits? Ada upper limit tak in
Of
terms of
course,
frequency?
dia akan seperti waveguide. It will behave just like a waveguide. It would have a limit whereby below that frequency, it won't be propagating anything. Okay, you say that is there any upper limit? Yes,
Mm-mm-mm.
the question is very very good, because so far, I would say, what is your frequency range? If you say 300 gigahertz, can you imagine how small the wavelength is? Very a few tiny is as a few micrometer or something. But it depends on what frequency range are you talking about. But within, if you talk about up to 60 gigahertz, yes, we can still propagate through the SIW technique. Just like I share in my slide, one of the application is at 77 gigahertz for the collision avoidance system, 77 gigahertz. So I think this is close to if you look at the terahertz, terahertz, 1 terahertz is 1000 gigahertz. So if you look at the terahertz, is about a few 0.7 or 0.07 terahertz. So it's still within uh, the reach of terahertz region. It's quite high for 77 gigahertz to be implemented. So still SIW have shown that capable of fabricating as high as 77 gigahertz. So still a lot to look at. So don't worry in terms of maximum limit of the SIW.
All right, Prof. This
Okay.
one from Gurmit Singh. It says, Prof, could you please suggest reference to start with SIW technology in antenna? Thank you for this session, he said.
Okay, thank you very much for the question. As if you're looking for textbook, there is no textbook I would recommend, but there is one monograph that was produced by me. I can share with you, or I can share the soft copy of the ebook or of all the monograph with the secretariat with Dr. Saidatul if you want.
Yes,
So
sure.
in there is some technique, some calculation that involves some design example that was used. So no problem, you can use it.
Right, sure. I think we get like one more questions
Okay.
from I think Dr. Rina. She
Uh-huh.
would like to ask, is it true SIW techniques can reduce undesirable radiations of the antenna?
Okay, good question because as you know, the nature of antenna that was fabricated using microstrip is TEM. The signal nature of signal that propagate through the technology is TEM and using microstrip technology. But if you consider to fabricate antenna using SLW, because for antenna is different nature with other devices. Antenna, you want to release everything. You want to like release. You don't want to hold any signal back. You want to release it all to propagate, to transmit. But for filters, you want to preserve the signal, preserve. So you don't want it to release in the air because it will create losses and some of the signal will not be passed through the second layers of devices. But two nature of different signal is there. For microchip is TM, quasi TM signal that propagating. Of course, the nature of TM is like quasi. If you look at the TM, is require minimum of two metal that require it to be propagating. But if you have But for waveguide, for TE or TM, it requires only one metal to propagate. Same goes with SIW. But you can mimicking the SIW same like the antenna, same like the microstrip line, by create an opening at the end of the SIW. So the signal will propagate, will radiate. Okay, but the radiation would be not as effective as in terms of radiation pattern, radiation efficiency compared with the microstrip, because microstrip nature is radiate. But for for SIW, the nature of the signal is confined. As you can see, the two possible signal that propagate inside the SIW or waveguide is either TE or TM. So these two nature of signals is not radiating in nature. But if you create an opening, create a slot, for example, or it can propagate just like what I would say the horn antenna, right? Horn antenna is very good in terms of high power. If you want to blast a very high power nature of, you use the horn antenna. It produce even higher power compared with microwave antenna. But in terms of efficiency, higher power, horn antenna is the best choice. But SIW you can try, but in terms of nature, my view for SIW would be lesser in terms of efficiency, and so that's back to the question, would be reduce the effectiveness or the nature of the, but you can still transmit any signal through making a slot or opening at the end. So it will still mimicking an antenna, but it's not as good compared with the microstrip antenna. Okay, I hope that answered the questions.
Thank you, Prabhat. I think that's
Okay.
all from the chat room. Is there any more questions from members of the floor before we close our sessions? But I think before we close our sessions, can everyone turn on their camera so that we can take a pictures? Rina cakap, okay, clear Prof. Thank you very much.
Okay, thank you, Doctor.
Boleh tak kita turn on camera and we take a group photo before we end our sessions? So ini pukul 4. Tukar layout. Okay. Mana tahu muka saya tak nampak. Okay, everyone ready? So saya cuba besarkan. Saya tak nampak kamera ke?
Patut tak nampak.
Okay, everyone ready? Okay, 1, 2, 3. Okay. Saya kena save dulu. Kamu tak save ni.
Okay, thank you very much to IEEE APMTTMC Malaysia section. I hope you can still continue this talk and so on, series of talk webinar. Congratulations to the current team now. Congratulations to Dr. Azremi, Dr. Haizal for the making great effort to make the microwave sharing is a knowledgeable event. I'm also participating in different talk by different speakers from different continent. It's very good. I hope we can continue this. Thank you also to Dr. Sai for helping me with the slides. Okay, all the best to you all. I hope you can success in every thing that you do. All the best to your future, to your career undertaking. I hope we can calibrate. We can calibrate in any research, any platform or something. You can get my email, my personal website with the secretariat. Thank you so much.
Right, thank you everyone. With that, we end our session. Thank you, and we hope to see you guys again in our next webinar, which is I think on next week. We have Mr. Nasir, which is from NASA. It's a good one.
Yes.
All right, thank you everyone.
Thank you. Bye-bye.
Bye-bye.
Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum.
Bye.